So cryptology is the, in the most general sense, is the study of making and breaking codes. So it is, so from a mathematical perspective, it is the study of designing and or breaking crypto systems using hard math problems.
Welcome to Superheroes of Science. I'm Stephen.
And I'm Sarah. We co-host Science from the Experts. Our guests are professionals doing cutting-edge science right now.
They're experts in their field discussing what they know best. So listen up and learn real science from real people.
Subscribe now and stay informed of our latest episodes and show your support.
Welcome to Superheroes of Science. Joining us today, we have Nick Egbert, mathematics PhD candidate here at Purdue University. So welcome, Nick.
Thank you.
So there's a lot of steps and a lot of research you had to do to get where you are now.
Yes.
And you've been doing it in cryptology?
Yeah. So I guess what I'm doing right now is like only pseudo related. It's more just number theory. But I guess it's also kind of hard to say like where like cryptology kind of begins and ends, because if you if you think about like what it means to do research in math, most people don't really know what that means at all, because math just already exists, right? Well, you could say the same thing about I think people are pretty okay with people doing research in chemistry. Well, the chemistry that you learn freshman year of high school is not all of the chemistry that exists in the world. Mm-hmm. More has been learned and developed over time, and the same is true for math. Like the math that mathematicians do is not algebra 2. That we have discovered things since then, and what is really nice about cryptography is it's basic on the theoretic side. It is basically just very pure math. It fills the like all of what I want out of learning about math, because I don't like messy applied things, because they're just kind of gross and they don't work very well, and it doesn't follow exactly the way you think it should, because the world is messy.
Now, when you say messy applied things, are you talking like when I would teach equilibrium and chemistry, and we had these awful ugly numbers, and it would be like just really nasty, like, oh, this is modeling a real world example of something.
Right. Yeah.
Okay.
Or so a good chemistry example would be like the ideal gas law. Like it's a very nice equation that like is absolutely false in the real world, right? Like you don't,
yes.
Like you never attain that, but it's like, but in like theoretically it's a very nice thing to have, and it's very it closely models the real world. And then so like there's all kinds of mathematical modeling of things that do their best to model the real world, but once you get into like mathematical modeling and applied math, you leave the nice like theoretical things, and then things just start getting messy, and it's no, in my opinion, it's no longer nice to do things. But cryptography, in the strictest sense, is still applied math, because it's so it is not just math, but it uses math. So by definition, it is applied math. But the math that it uses is very much, it's kind of like very pure mathematics. And then in particular, like number theory. So there's not like, really messy equations. Like you're talking about, factoring integers. So if you factor an integer, your answer is also an integer. So you don't like, there's no messy decimals. It works out very nicely. And so but it has a very important real world application. So for example, this call that we are on right now is encrypted. So nobody besides us, and I think Zoom is end-to-end encrypted now. So not even the company that owns Zoom can intercept this and like see what we're talking about today.
Oh.
So it's the reason why you can deposit a check with your phone, right? You would like, it would be pretty bad if you could do that and somebody could intercept that message and somehow mess with that. Those are things that you would want to keep private. Your logins to any website you want to keep private, especially if you engage in the very bad practice of reusing your passwords. And if your Amazon password is the same as your bank password, and somebody cracks the Amazon, a list of Amazon passwords, and they try that on all of everybody's bank accounts, and they get into your bank account, like that would be a very big problem. So we definitely use cryptography to try to avoid some of those things as well. Like two-factor authentication is a big thing as well, so that you avoid that just relying on that single password.
All right, so when I think of cryptology, I'm thinking of movies, okay? And so it's always just some kind of code, math code. And then now you're telling me, oh no, that's used for your passwords and even encryption and stuff we're doing. I never thought of that stuff being cryptology. So you're broadening my understanding of
pretty much everything that you do is encrypted. Everything that you do on a computer is pretty much encrypted to some degree. So for example, if you have an iPhone and use iMessage, that is end-to-end encrypted. So like you type your message in plain text, but then before it runs through Apple, it is encrypted with some sort of key that you've agreed upon with the person that you're messaging, and then it runs through Apple's server. But Apple is not able to decrypt it, and they just pass it along to the other user, and they have the key to decrypt that message. Passwords are also generally, or they should be encrypted. It is a very bad thing if you are some sort of server and you have people have a username and password to get into your system, and then you store the passwords in plain text. Because if somebody breaks into that list, they just see everybody's passwords. So that would be a very bad thing to do. And it's very uncommon at this point. But if you use any sort of service where you say you forgot your password and they email you your password, that means they didn't encrypt it because they know your password.
Oh.
I've recently gone through something like that. I had to get a new phone, and I had to re-sign in a lot. My phone had saved all these passwords, and I'm like, oh, I don't know my password. I have to log in. And I've noticed every single one of them, I click on forgot password, and it sends me a link to make a new password. It's not just sending me, where's my username? If I click on it, it sends me what my username is, but it won't say what my password is. So this
right. Yeah, that's precisely why. So what they typically do is, I think they probably store your username in plain text, but then their password, they store what's called a hash of your password. So it's a special kind of cryptographic tool that it's a one-way function. So they can so like you give me your password, I apply this function to it, and then it spits out a fixed sequence of numbers that kind of is like a digest of what you gave me, and so every time you give me that password, it'll spit out the same result every single time. But if I have that result, I can't reverse engineer it to figure out what your password was. And then if you mistype by one character, and then I run it through that same function, it's going to spit out a completely different output. So every time that you send me your password and I run that, I get the same output every time. And if you change the input, that's going to change the output. So that's a very important property. But yeah, so they can always check, are you putting in the right password, but they can't figure out what your password is.
Oh, I had no idea it worked that way.
Yeah,
Makes me feel a little bit better.
I know.
But you hear of big data breaches and stuff like that, where your stuff was, you know, they're like, oh, you have to change password stuff because some data breach. Why is that?
Right. So that's so sometimes that's just out of precaution. Like if it's just so if they're only storing hashed passwords, then it also depends on what hash function they are using. So there's so if you ever read like any sort of like encryption related news, you may see the word SHA, which in all caps, which is SHA, which is secure hash algorithm. So there's there's one that's called SHA-1, which is broken. It's very insecure, and so if they're using that one, and there's a couple others that they could be using, that if they're using it, they are reverse engineerable. Like they've been cracked, and so if somebody knows the hash, like the hash values, they can figure out what the original values were. There are bigger ones called like, I think the most common one used now is SHA-256, and the 256 means that the output is 256 bits. So it's a string of zeros and ones of length 256 is what the output is. So the number of possible outputs then is, 2 to the 256th power, which is a very large number. So 2 to the 256. So that is on the order of 10 to the 77th power.
Okay, and I've heard of like 256-bit encryption, and that's what they're talking about.
Yeah. So when you're talking about, so for the hash algorithms, they're talking about the length of the output. For encryption, they are talking about the length of the key. So the way that typically works is, if I click on, does it tell me what? Oh, it just says encryption is enabled. That doesn't tell me how, like what kind of encryption. Oh, no, okay, so this says, our connection right now is using AES 256. So that means that it's using it's the advanced encryption standard. And then 256 means that the key length is 256 bits. So AES is a form of symmetric cryptography. So that means, there are two different like major types. So you have symmetric and asymmetric. And so our connection right now is using a symmetric key, which means we both have the same key, and we are using the same key to encrypt and decrypt the data. So my feed is being encrypted with this key, send it over to you, and then you're decrypting it with the same key. And the way that you accomplish that is a computer just reads everything in terms of ones and zeros. And so the information is encoded in some way to a string of ones and zeros. And then we use this key to it's called XOR. So that's exclusive OR. So if I've got 1 0 1 1 0, so say that's the message, and the key is 0 1 1 0 0. So if we were to XOR that, then you basically just add them, but 1 plus 1 is going to be 0. So that's going to be 1, 1, 0, 1, 0. What's nice about that is if you do it again, so if I take the key and put it back there, so 0, 1, 1, 0, 0, and then we XOR that again, we get 1, 0, 1, 1, 0. So we get back to where we started.
Yeah.
So this right here, that would be the ciphertext, and this the original message. So in plain text.
Okay.
And then this being the key here. So if we both know the key, I send a message that's just a string of 1s and 0s, and then I use that key by just doing this XOR operation, and then I send, and that creates the ciphertext, and then I send that to you. And since you also know the key, you can decrypt it to find the original message by doing the same operation again. So that's the basic way that symmetric cryptography works, or symmetric key cryptography. So we both have the same key, and we use it to encrypt and decrypt. But do you know what might be a problem with, so we both have the same key, what's a potential problem?
Well, if anyone got that key, then they would know it, decode it.
Right. So how do we have the same key without anybody knowing it?
I don't know.
Right. Because the whole basis of having this secure connection, that if somebody's trying to listen in, all they get is the nonsensical ciphertext that they can't figure out what it means. Well, in order to establish that, in order for me to give you that ciphertext, we had to agree on this key. Well, but in order to agree on a key, our connection had to be unencrypted, because otherwise you wouldn't know what the key is.
Yeah.
So that's a problem, right? So that's why we have asymmetric cryptography, asymmetric key encryption. So we need a way to agree on a key where we assume that somebody is listening on the line, and so we need to figure out a way to establish this key that nobody can. So we can both agree on a key without the public listening and figuring out what that key is, and so that's where asymmetric comes into play. So I think at this point, one of the most common ways that it's done is using a variation of the DiffieHellman protocol using elliptic curves. And then the other most common one is using RSA. So RSA, so that stands for Rivest, Schrdinger, and Eelliptic, the three researchers that developed it back in 1977 is when they published their paper, I believe. And then Diffie and Hellman published their paper in 1976. So the Diffie-Hellman paper was the first public paper on public key cryptography that was published. So it was later discovered, or I guess revealed in the late 90s, that the British intelligence agency, GCHQ, had developed similar algorithms in the late 60s, but it was classified, so the world didn't really know about it. So the people that developed it in England did not get credit for it, because it was only internal at the time.
And this is a way of coding information so other people can't read it.
So for the DiffieHellman protocol in particular, what we do is we'll agree what so we use the analogy is with paint. So we'll agree on a public color. So this is going to be public, and so we'll say so this isn't going to be perfect because I'm not going to know how these colors mix together. And so we're going to pretend that what colors I choose are going to mix to the colors that we pick. So this is agreed upon in advance. And then so then we each pick our own private colors. So say I pick, this and then Sarah picks this color. So what we do is I'm going to take equal parts of my color and the public color and mix them together. And I'm going to get a pretty brown color. And then Sarah's going to get a nice red orange color. So then we mix. So then bring that down here. So we mix with and then we're going to exchange. And so this is done publicly. So anybody listening can see our mixed colors, but the problem with mixing paint is you can't unmix it, right?
Yeah.
So that is a very much a one-way thing. And then so now I have Sarah's paint over here, and I'm going to add my color in there, and then Sarah's going to take mine and add her color.
Mhm.
And this is how we create our private key. So we both have the same result,
Right.
but we don't know what each other started with. We only know what the agreed upon public thing was, and we know what the first stage mixing was, but we can't. So then the problem to break this would either be given the public so the problem to break this would be given these public mixed colors, can you figure out a way to derive the shared secret, or can you figure out a way to like go up one step and figure out what the individual secret was? But
that's a little next level. Okay.
Yeah. So that's the analogy using paint, and the way that it's done using elliptic curves is you're basically you're adding points together in some sort of weird way, and that's used to derive a shared secret. So what does that look like? So here is what an elliptic curve looks like. So it's just, so an example would be something like, say like, y squared is equal to x cubed minus 1. or no, I think that minus x, I think is what this one is. So if you were to, given that equation, if you were just to plot that using the graphing calculator, it would look something like this. And then, so they kind of come in two flavors. Either you have, so you always have this right part right here, and then whether you have this oval shape on the left-hand side or not depends on whether you have 1 or 3 real solutions to your equation here. So you have, so you always have at least one, because it's like you've got it, because you've got to pass through the x-axis here with this because you have a cubic equation on the right hand side. But you either have 1 or 3 real solutions. So if the right hand side will always factor as a linear term times a quadratic term. And then if that quadratic term can factor in terms of real numbers, then you get the extra oval bit over here. And so it may seem really weird that you can relate this to what we were just talking about, but the way you start with it is first of all, you got to decide like what it takes to have like some sort of like addition going on, and then the eventual punchline is that we want to we want to add points together in some sort of way that is kind of irreversible. So the way that you would add 2 points together here, so if I pick a point P and a point Q here, and then I draw the line between them, that's going to intersect this curve at a third point. And that's something that's always going to happen. If you accept that, if you, in the event that you don't, the other point is at infinity. So if you think about the fact, so like this kind of goes, you know, up and down forever. So if you think about, if we could take the top of the y-axis and connect it to the bottom of the y-axis, then these points over here would kind of reach each other, right? So then, so any time that you don't visually see it intersect, then that's where the third point is. And so any line that crosses a curve like this is going to hit it at 3 points. And then so we draw that line, and then we will draw a vertical line here and see where it intersects down here. And this is going to be what we call P plus Q.
That's what I'm looking at. Break this down for me, because you're so far out of my area and over my head now. And so, and this is used in what type of encoding?
So this this is used to so this is how like this paint example is used in practice is excuse me. So like after you've established like how this like addition works, what you want to do, and so instead of having a secret paint color, what you're going to do is you pick a secret number, a secret integer. So we'll say A, and then you compute A times, you know, a point P, which is you just add P to itself, A times.
Okay.
So using this really weird addition law, if you so you have your secret integer A, and then you so you compute A times that point, and then so I guess to be exactly like the previous example, so then and then Sarah's going to pick a secret integer B and do the same thing, and then we share those results, and then I'll compute so I'll add Sarah's shared number A times, and then Sarah will add my shared number B times. Well, if you add it, I mean, just think about with numbers, like if you add something to itself B times and then A times, or if you add it to itself A times and then B times, you're just adding it to itself A times B times, right? So this is, so both of those are just, both of those are the same number. So, so we have this similar setup, and the reason why that's going to be difficult to undo that in this case is, instead of having a pretty picture like the one up here, you're going to take your elliptic curve, and you're going to like whenever you do your operations, you're going to do it modulo some prime number. And so what that means is you're going to, like, every operation that you do, you're going to take the result, divide by the prime number, and take the remainder, and the remainder is what you keep, and that works out very nicely, and it's all very consistent, and like it so that it nothing gets lost, and the same result happens every time, and that's what makes it hard. That's what makes it hard to recover what the original point, or what the original numbers were, because you're cutting off some information. So if we didn't divide by some prime number and take the remainder, then it would be reversible, because you would just like, you just need to know how many times do you add P to itself to get the this end result. That would be very easy. But since you cut off some information, it's much harder to reverse.
And so here you're talking about the difference between what we were first talking about, that symmetric cryptography. This is that asymmetric cryptography. Right.
Yeah. So this is primarily, but it's very slow in comparison. So it's primarily used to derive a shared secret, and then you create a shared symmetric key using that secret. So what typically happens is, so the fact that our connection is using that symmetric key right now, that means that we either we used this this algorithm, or the RSA algorithm, which is a bit different, or quite a bit different rather, and we use this asymmetric key algorithm to agree on the secret, and then there are certain algorithms that are used to, like, given the secret, derive a key. So there are like certain functions, like standard, like there's like a list of standard functions that are used, and so they're secure in the sense of, like, the the input is very random. So even though the like you're using the same standard list as like everyone else in the world, the fact that your input is radically different from everyone else's, the output is going to be completely different. So it's not something that you can really reverse engineer, and then that is then used to create this symmetric key connection, so that you don't have to go through all of that business every time, because because there are some potential attacks on things like this, where like if you're using the same process every time, then over time, like certain things could potentially be leaks that could lead to people trying to attack on this. But if you only use it once to create this symmetric key, that is just this random sequence of ones and zeros that nobody knows, then once that so then we just kind of forget about that asymmetric business. Then so if that's only used once, the likelihood of that being attacked and then used to break things is much lower, versus we're using this the same symmetric key over and over. Like it's I mean it's kind of crazy to think about, but like every second of what we're doing is like, so it's like continuously encrypted and decrypted over the internet. So
yes.
if you had to do this asymmetric thing over and over again, that would greatly slow things down, and you would probably have a lot more lagging involved. Like even if you're just talking on the order of milliseconds, that's enough to make somebody's mouth be a little bit off and very hard to follow.
Okay. Wow. Now, I would have, originally when I thought, okay, for encoding data, I would have thought, oh, well, that's a computer science type thing. And then I had not considered it all being it's all math. I had not thought of that.
Yeah. So so there are kind of two components to it. So it is very much a bridge of computer science and math. So the theoretical design of crypto systems is very much a mathematical sort of endeavor. You do get some CS influence, because unlike in pure math, when you just care about a solution and you don't care about efficiency, efficiency is kind of important for cryptography. If it takes a really long time, it's not very usable. So the algorithms definitely need to be efficient, but they need to be irreversible. And so the main two that we use today are mathematically not, or I guess I should say they are not known to be mathematically reversible. I guess it is possible that somebody has broken one or both of them, and that knowledge is not public. But that is unlikely, because there are so many people that are publicly trying to break it, that the likelihood that because they like that that community is so far away from having cracked it, and the private, like probably intelligence communities of various countries that one of them has cracked it, I would say is pretty low. But it has been cracked if quantum computing becomes a thing. So you probably hear a lot about that, and like at least in like science news, where people talking about quantum computers. And I think I think maybe Google has the best one right now. So there's a couple in the United States that are that have advanced quite a bit in the last few years, and then a few other countries have made improvements. But there is an algorithm that works on a quantum computer that would break all of our asymmetric cryptography that is used today.
Really?
So yeah, so that's called Shor's algorithm. So it's so RSA is based on, so the key in RSA is based on a number n that is a prime of that is a product of two primes. So the math hard problem for the RSA crypto system is the fact that it is hard to factor integers. So there are a few algorithms for factoring integers, and for small ones, the easiest thing to do is check, is 2 a factor? No. Okay. Is 3 a factor? No. Okay. Is 5 a factor? And working your way up that way. That like if your integer is, say a few hundred decimal digits long, there are a lot of prime numbers to check in that range. So I guess you'd only have to go up to the square root at most, I guess. So, but if you're, so say your integer is 500 or so digits long, then the square root is still 250 or so digits long. So that's still a very big number, and there are a lot of primes in general. So it's just too big. So the numbers are too big to check like that. There are smarter algorithms that exist, but they are still they are sub-exponential algorithms, is what it's called. So they're when you talk about complexity of algorithms, there are 3 classes. There are polynomial, and then exponential, and then sitting in between them is sub-exponential. So if something takes polynomial time, is generally interpreted as being quick. Something that takes exponential time is extremely slow, and in the long run is basically impossible for a computer to do. And then sub-exponential, I mean, is like literally everything in between. So it could be, in practice, it could be something that's very fast, but it could also be something that is extremely impractical or slow. So the best algorithms that would break RSA right now are sub-exponential. So they are relatively hard to do in practice, especially if you just make the key bigger. So that's one way to counteract it, is if you make the key bigger, well, now your search space is much bigger, and so that increases the length of time that it takes for the algorithm to work. And so you can change what was maybe hours to years or decades, or even longer, just by changing the length of the key.
Mm-hmm. So it comes down to computing power in the end. Is that what I'm hearing?
Yeah. And so, but Shor's algorithm is a polynomial time quantum algorithm. So if we have quantum computers at the level that is required for Shor's algorithm, which there's some sort of theoretical like lower bound number of quantum bits that you need to be able to implement Shor's algorithm. We are the most conservative estimate is like we are at least 15 to 20 years away from achieving that. But it's still a problem, because the stuff that we encrypt today will still exist 30 years from now. So if you are, I don't know, maybe a government that has secrets, i.e. every government in the world, you don't want to protect your information using something that could be cracked in 20 years. So we need a way to protect information, like it's a problem today, even though it's a problem in the future. And so there's actually so NIST, so that's the National Institute for Standards and Technology, is currently running I don't think it's supposed to be called a competition, but it's a competition of post-quantum crypto systems. And so they're currently, I think they're currently revising like the third round I don't want to say contestants, but the third round like algorithms that are still under consideration. And so they, I think those are like, so they've divided up into like, I think there's like the current finalists, and then there's like alternates, just in case some of the finalists don't pan out. And then, so by 2024, they are looking to have set standards for algorithms for encrypting information that is resistant to a quantum computer. And so in terms of like a normal everyday application, you will notice nothing. In the same way that you have never noticed how your internet traffic is encrypted, you still won't notice it. I think most of these quantum resistant algorithms are much slower, so you'll probably you may have some latency, but like it should be minimal. I know that a couple of years ago, so Google has a browser that is for like kind of like beta testing various things called Canary. And on that browser, they implemented one of these post-quantum algorithms for encrypting your internet traffic. And so it was so there's quite a few users that use this for testing things, and there was no meaningful latency with the algorithm that they used. So that was promising, because if you get frustrated with the internet being slow now, if whatever they use to encrypt it 10 years from now makes it slower, that would be even more annoying. Yeah, they're the ones, I think the ones that are faster, if I remember correctly, have more potential for being cracked a little bit easier, and the ones that are a little bit more robust against cracking are much slower. So like you got to kind of find the right balance there. But they also some of them also require much larger keys than even what we use today, and some of them require much smaller keys. So there's so you have to balance security with memory and speed, and figure out what's the best approach there. And that's very much a computer science problem.
So to be a cryptologist today, I mean, much different than it was 100 years ago. And tomorrow sounds like it's going to be even different than today. So do you pretty much have to have strengths in both mathematics as well as some sort of coding? Or can you just do the mathematical side and have a counterpart do the coding part?
Yeah, so there's so there are I would say 2 to 3 or so avenues. So you could very much just be a mathematician at a university in a math department that does research and the kind of the number theoretic side of cryptography, and you come up with these systems that may or may not be implementable. So there are quite a few crypto systems that exist on paper that you could never use in practice. But and then so it would be the job of a computer scientist to or a mathematician that is much closer to computer science to figure out like how exactly you would implement it. And so so like for example, for this like NIST competition, they I mean, you have teams of at least half a dozen people on any given algorithm, and so you've got so some of them are just the more mathy people, and I think they also have CS people involved because there's another area in cryptography called cryptanalysis. So that would be the study of trying to break crypto systems, which is an important field of research, because if as the person implementing these crypto systems you don't research it, well, the people that are trying to steal your information would be researching it. So you need to make sure that the systems that you design are secure. So there are two possible avenues that you can attack a crypto system. You can attack the mathematical problem that is underlying the crypto system. So for RSA, you're trying to crack the problem of factoring integers. For the Diffie-Hellman example, you're trying to crack what is called this discrete log problem. So if you think about if you have a number, a to the b is equal to c, right? Then that means that log base a of c is equal to b. So if we're trying to find b, if we can compute the logarithm of c. But in this world of modular arithmetic, so dividing by a prime and taking the remainder, since you lose some of that information, you can't just take a logarithm and figure out what the exponent was because of the information that was lost. And so that's why it's called a discrete logarithm, because we're only using the numbers between 0 and this prime number -1. So that's where the discrete part comes in, and so that is the underlying hard math problem for this elliptic curve Diffie-Hellman protocol. And so you could try to attack those mathematical problems, and that would break the crypto systems. But a crypto system is also a real world thing that is implemented on a computer. So you could try to attack the actual like physical implementation. So in the an example using RSA would be, so the basic way that RSA is going to work is you take so you're going to take your message and raise it to some exponent, and then you're going to divide by some number n and take the remainder. So this modular exponentiation is the main mathematical computation that is done. So the standard algorithm for doing this is called square and multiply. So if you take your exponents and you represent it in binary, so as a string of ones and zeros, but so it's so an times 2 to the n plus an minus 1 times 2 to the n minus 1 plus a1 times 2 plus a0. And so each of these a's are either a 1 or 0, and then so you're just expressing this exponent as as a sum of powers of 2. So you can do this for for any number, just in the same way that our base 10 number system. So if I write the number 137, right? That means 1 times 10 to the second power plus 3 times 10 to the first power plus 7. So you can writing it in terms of powers of 2 is like you're just changing the base of the number system, but like all of the numbers are still equally representable. Right. And then so based on whether so it has to do with whether each of these A's is either a 1 or a 0. This tells you whether you want to take your number and then square it, or take your number and then multiply it by m, just to make it efficient. So instead of just multiplying it by instead of doing m times m, e times, you can speed it up by whether you have these odd or even powers of 2 are in this expansion or not. But so the physical attack that if you were to implement this poorly, that could happen is to multiply an integer by an integer takes a different level of computational power than squaring an integer. So if you have some sort of way to listen to the computer and maybe you can read how much power is being used or something, that'd be a good measure of what the computation is taking. If you can read off these peaks of more power was used here and then less power was used at each of these stages, then you could reverse engineer, this was a square, this was a multiply, square, square, multiply, and then you could recreate the exponent just by listening to what the computer was doing.
Oh, wow.
But a way to combat that would just be always square and always multiply at every stage, but only keep which one you need. And then so you use the same level of power every single time, right. But because it doesn't take any power to save. So what used to be like a kind of an up and down kind of power reading is now kind of a more of a straight line, and it's much less readable. So that's called a side channel analysis. Oh gosh, channel. Does that have 1 and there 2?
2.
2. Okay. Side channel analysis. So that's where you're listening in some way to the implementation of the cryptography and trying to break it in a physical way. So that's another thing that has to be kept in mind when designing these things. And so that may or may not be a math problem, because so the solution to what I just mentioned is more of kind of computer science solution. Okay, just do the same thing every time. But if there is, but I think there are definitely some side channel attacks that you could come up with where the solution to it may be to mathematically change the whole process to avoid that. And other solutions would be more like this one, where you just change the physical implementation.
Thank you for listening to this episode of Science from the Experts from Purdue University's Superheroes of Science.
If you like this episode, subscribe, give us a positive review, and share the love. Boiler up!
Hammer down.